Okay, so welcome to our seminar, and it's a great pleasure to have Professor Romeo Ortega here to talk about his recent work. So many of you would have known him already, but I will give a very brief introduction. So Professor Romeo Ortega was born in Mexico, and he obtained his bachelor's degree from National University of Mexico and Master of Engineering from Polytech Institute of Leningrad, and a doctorate degree from Polytechnical Institute of Grenoble in 1974, 1978, and 1984. He then worked at National University of Mexico until 1989, and after several visiting professorship positions, he joined in 1992 French National Research Council, and he worked there for 28 years until 2020 July, and then he joined Mexico Autonomous Institute of Technology, where he's currently a full professor. He's also a distinguished professor at Itimo University in Russia, and his research area are in the field of nonlinear and adaptive control, with special emphasis on applications. He has published 5 books and more than 385 papers with an H-index of 95, and he supervised more than 35 PhD students. He's a fellow of IEEE and a fellow of IFAC. And he served as chair for several IFAC and IEEE committees and have been sitting on editorial board for many journals. He's currently editor-in-chief of International Journal of Adaptive Control and Signal Processing and senior editor of Asian Journal of Control. And without further delay, Romeo, you can please make start.
Okay. Thank you very much, Bing. And I apologize for this, as expected, confusion when I'm very clumsy with computers. So I you will be able to follow me and understand what I said. So there's a button on below that says plus or minus, so I cannot control the slides, can't I?
Sorry, would you like to give a try? Would you like to try it?
Well, I cannot move the slides. So
okay, so I will do it if you just let me know. Shall I go to next slide or?
Okay, fine. Okay, so as you can see, the title is a little specialized subject, which is essentially adaptive control and parameter estimators and systems parameterizations. And the main objectives are the 2 points indicated there. So talk about robust parameter estimation, mainly concerned with removing persistence of excitation, and some new results on reparameterizations. And we are particularly interested in systems which are non-linearly parameterized in non-separable ways. And at the end, I would like to give some very brief thoughts about some present challenge in adaptive systems theory and profit from this very big audience and specialized people, and give you my personal opinion about what's going on in the field. So can you move to the next one, please? Bing? Can you hear me, guys?
Yes, I think that was a little bit delay, but now, yes.
Okay, I'm sorry. Yeah, okay. Well, communication with Mexico is not Europe, you know. Okay, so this is the layout. First, I will talk about robust defined adaptive systems, then about nonlinear parameterizations, and at the end, I would like to talk about these trending topics and classical problems that I believe are somehow open and what people are trying to do to solve them. So can you put next slide? So first, let me talk about robust defined adaptive systems, and the main concern, as I said before, is trying to relax this stringent condition of persistence of excitation. And next slide. So what is this persistence of excitation assumption? Is probably one of the most important results in adaptive control due to several authors, and basically says that the error equation that you get with classical estimators, like for instance, be globally exponentially if this vector, regressor vector that depends on signals from the system, satisfies a condition which is persistence of excitation. I will give you the definition. It is basically that you are spanning the space consistently in time. So the challenge is to ensure parameter convergence by exponential stability without this assumption. So that's the main challenge. And there are many motivations to relax it. First of all, it is a highly restrictive assumption. So it's not satisfied if you do regulation. Also, the robustness of adaptive controllers, the existing robustness claims is really a continuity claim. So we don't have a really robust in the sense of linear robust control. So the only way to have robustness is to have exponential stability, which in turn means persistence of excitation. And also there are many applications where you need parameter conversions. You want to estimate, I don't know, for instance, the maximum power point extraction, and you want to estimate points of the graph or so on. So you need a parameter conversion. So that's the main motivation. Next slide, please. So what can we do to relax persistence of excitation? To my knowledge, the first results were in concurrent learning and composite learning. That was in 2013, 2018. And there are some precursors to this research, which are somehow related with this result, which is somehow storing all data, past data, and using the past data in the current estimator. That was done in the past by Kraussing, Hargonekar, myself. And in composite learning, it is motivated by the work of Slotin and Lee and Duarte and Arendra that proposed this idea of combining direct and indirect depth control, but with a very special twist that Professor Pana and Hoop introduced in Automatica, which is a very interesting result. So the idea is to replace persistence of excitation, which is to the left of your next equation, and replace it by something which is called excitation on an interval, which is a much, much weaker condition. So you only need to span the space on a window of time. This was a concept introduced by Kreiseman and Ritz in the 90s. And I could recommend two tutorial papers by myself and my co-authors and by Gu and Pan. So the recent result, which is quite interesting by Wang and co-authors, is that persistence of interval excitation, is equivalent to identifiability of a linear regression. So, and identifiability is a very well-known concept. It's in the book of Goodwin and Sim. It's just the possibility of collecting a certain number of measures to complete the rank of a matrix, and then you have a unique solution to the algebraic equation. So it turns out that this is equivalent to interval excitation, and that's, I think, a fundamental result. Next slide. So there are other recent results. Myself with Nikita Barabanov and Laurent Prali, we gave some weaker conditions for persistence, weaker than persistence of excitation, sacrificing the exponential qualifier. So you only get global asymptotic stability. But these results are still very technical and hard. Personally, converters by Cruz and co-authors, but they introduce a concept is called weak persistence of excitation, but it's still a highly technical condition, and it's applicable only for least squares without forgetting factor. So we know that without forgetting factor, least squares stops working, so you lose alertness. There's some recent results by Marina and Tomei on analysis, mainly non-computable analysis, which is similar to what had been done before by Boyd and Sastry, what they call part convergence. There's a very interesting paper by Dean in Systems and Control Letters, which generalizes least squares in a very, very many free functions. And he introduces a concept that he calls T-star excitation. And there's a version of T-star excitation which relaxes PE, but the problem is again that it loses alertness, just like least squares without forgetting factor. Then there is a recent result by Carot and ourselves, where we combine a method that we call generalized parameter estimation based observers. Is some developments for observers. We combine this with adaptive control and introduce a scheme that is exponential stability with only interval excitation. And recently with Professor Aronofsky from Superlec, we generate a new linear regressor equation, which is PE. But the scheme is quite complicated. And there's also a final version of one which combines again this GP with gradient estimator to replace PE by IE. But to the best of our knowledge or our personal opinion, is the strongest result is in the next slide. Please, next slide. And next slide, please. Can you put next slide?
Sorry, Romeo. I think I have put it next slides. This dynamic regressor, is this slide you want?
Wasn't there a slide 7?
Yes.
Okay, so this slide, well, it just gives you the references for the scheme that I want to discuss now. So we go to slide 8.
Yep. We are on slide 8. Yeah.
See, the idea of this estimator is to combine least squares with a classical gradient. And the main component is something that we call dynamic regressor extension. So you have a nonlinear parameterization that the one given on top, y equals phi transpose g theta, and you want to create, where theta is a vector of dimension q, yes, and you want to create, sorry, P, and you want to create Q. There's a mistake there, sorry, should be Q. You want to create Q scalar nonlinear parameterized regression equation. Because if you create scalar, then you have a very strong result for convergence. And there are two components. First, something called regressor extension, where you want to replace this scalar y equals phi transpose g by a matrix relationship. This is not new. This was introduced in 1967 in the literature of signal processing by Lyon, and then was used by Krassenmeyer in transactions. And the idea is, as I said, to create a matrix relationship, capital Y equal capital phi G. And these are matrices, phi is a square matrix. And next slide. Next slide, please.
So we are on slide 9, Romeo.
Yes, please.
Yeah.
Slide 9, yes.
So I think there's some delay. Here it's on slide 9, so probably you will see
I'm
now.
sorry. I'm sorry. It's always my fault. I know.
No. Do you see slide?
You have this.
Yeah. Okay. Yes, please.
I'm still in 8.
Oh, yeah, still on 8. Here is. Okay, how about this, Romeo? Would you mind if you turn off your camera? That will probably save some bandwidth.
Yes.
Yeah.
Probably you should switch off camera.
Yeah.
Just to increase bandwidth.
Yeah.
Romeo, could you switch off camera?
Switch my camera?
Off, yes.
Yes.
Yes, and now probably the speed connection will be faster, because we see slide 9 right now.
Okay.
Okay. But you still see the slides?
We see slide 9.
Okay. So now the next step is this so-called mixing, but it's a very elementary operation. You just multiply this matrix relationship by the adjunct of the matrix phi, and then you use this equation that says that joint times matrix is the determinant times identity, and then you recover your scalar relationship. So this is the key step, adding this mixing step, which is the part, as we know, first time this is used. And then you can invoke properties like monotonizability, which was introduced by Demidovich in the 60s, and you can prove that you can exploit this property if you use these scalar relationships. But you cannot exploit it if you have a vector relationship like before. Okay. Next slide. And next slide, please.
So we are on slide 10.
I'm still seeing slide 9.
Romeo, probably it's better if you will follow yourself for slides. You open presentation on your computer and follow by numbers. So you may see slide 9. We see slide 10 right now.
Yeah, I see slide 10 now. Yeah, I see slide 10. Yeah.
So some delay, yes, disturbance.
Yes, I'm sorry again. Okay, so now what are the convergence properties of this scheme? Now you have a scalar relationship. Notice the subindex I. So you can solve this scalar differential equation and you get this solution, which is this exponential gamma I integral. And then you get some two nice properties. You get some individual parameter error monotonicity, and you also get an equivalent condition for convergence, which is simply that this scalar delta, which is the determinant of this vector, this matrix phi, should be non-square integrable. And moreover, you can make the convergence arbitrarily fast by just increasing the gamma. Moreover, if delta is PE, so it's more than not in L2, then the convergence will be exponential. Okay, next slide. Slide 11, please.
We see 11 slide, come on, we see 11.
You see 11, well, I don't see 11.
We're already on 11th slide.
I see slide 10.
Please, Romeo, you may open slides on your computer, not follow by Microsoft Teams, follow by yourself and switch and control slides yourself on your computer, and Bean will repeat.
Well, I cannot because I see slide 11 now, okay? So this is the reference I wanted to talk about. So can you please show
We are on 12, Romeo.
You are sorry, what?
We are on slide 12.
You have 12 now?
Yeah.
I have 11. I'm really sorry, this is a mess. Everyone is seeing slide 12?
Yes, Romeo, we see slide 12, and I propose to open PDF, open Adobe Acrobat, and just open your file, and you will follow by yourself on slides, and we will follow thanks to Bean the same slides. And, and you will see 12 on your computer. Not from. Just open your PDF.
Now I see 12. I see 12.
Okay.
I think
and
it's just,
12 as well.
It's just a delay. I think it's a problem of a delay.
Yes, indeed.
Okay, so slide 12 is the description of this least squares plus DREM estimator. And the main idea is to replace this operator that created the extended regressor by simply the matrix, the covariance matrix of least squares. So if you look at the first two slides there, this is exactly least squares with the matrix F being the covariance matrix. And then comes the mixing step, which creates this delta, but now multiplying by this matrix, which is the IP minus F0F. And you can prove, if you can put in the next slide, please. Do you see next slide? Okay, so the key step is an observation made by Philippe de Larminat in 1984, where he proved that this matrix F minus 1, the parameter error, which in this case called G tilde, is invariant. So you take that you establish a relationship between G, some measurable signals, which are capital Y and capital Phi. So with this new extended regressor, you don't need to add any operators, but just the least squares itself will ensure that you have the extended regressor. The extended regressor, capital Y equal capital Phi times G, and then you get all these nice properties of the DREM scheme. That if you have the I condition that ensures delta is larger than 0, then you have PE. So actually, if you use this scheme, you will get something more than just not L2. You will get persistence of excitation. Consequently, you will get exponential convergence. So I think let's move to the next slide because I'm running out of time. So slide 14. So I would like to start talking about parameter estimators for non-linearly parameterized systems. Next slide. So then there are basically two tasks. You have a nonlinear system, which is non-linearly parameterized, and you want to estimate the parameters. So the system sigma, and you want to construct an estimator that creates this estimate theta hat, such that you get some kind of convergence, hopefully global, exponential, and so on. And it's the same problem if you have just a static map. So the second task is in the next slide, is now you use these estimators to do indirect adaptive control. So you're going to replace a supposedly full information controller that we call U star, and you replace it by some U with theta hat replacing theta, and you want to prove that even theta by theta hat, you still have some properties of the parameter error using the estimated parameters. This is the classical scenario of indirect adaptive control. So next slide, please. So now the key step to solve either one of these problems is to derive some kind of regressor equation. And because of the availability of this least squares plus DREM, we can deal with nonlinear parameterization. So that's a big difference with standard scenarios where you're forced to use or rely on linear regression equations. So notice that now you have a map, a capital G of theta, and there are actually two different levels of complexity. Either it is separable, which is where you can separate the measurements from the unknown parameters, or non-separable. And non-separable is, unfortunately, is very common in practice. For instance, you have exponentials, you have sinusoids with unknown frequency, and these appear very common in applications. So there are very few results on non-separable nonlinear parameterizations, and I would like to talk about that. And even though you have if you have a separate parameterization, you could say, well, I can over-parameterize. I can test this G, or treat it as if it were a new, bigger parameter. But you know that there are very big prices paid for over-parameterizations, lower convergence, and so on and so forth. So next slide. So for non-separable, nonlinear parameterized regression equations, there are some results. For instance, for the estimation of the frequency, it's an old problem that was solved in 1999. We can exploit convexity that I learned from Sasha Fratkov and his great book, Fomin, Fratkov, Yakubovich. You can mix convexity and concavity that was exploited by Anna Swami and co-authors and Tukin and so on. Or you can use monotonicity. So actually ourselves, we adopted the immersion and invariance approach for estimators, and we exploited monotonicity. So let me just show in a couple of equations the difference between exploiting convexity and exploiting monotonicity. If you use convexity, the kind of estimator that you will implement is the one that is on the bottom line. And then you can prove that you get a good descent, so theta tilde times theta tilde dot smaller or equal to 0, only in some subspace of the parameter space when this inequality is satisfied. And this inequality depends on time. So that and concavity and switch and so on. While if you use monotonicity, you will always get a decreasing parameter. So for all regions in parameter space, you get theta tilde transpose theta tilde dots more equal to 0 always. So in that respect, monotonicity is a better choice if you have it. Next slide. So let me talk a little bit about systems with non-separable parameterizations, and this is going to be reported in the next CDC. It's a very recent result. Next slide. So let me give you an example, so you just get the idea. So let me take a scalar system, very simple system, F1 plus F2, and then some, and then you have this nasty exponential term, e to the h2. So the idea is to combine the equations via differentiation, integration, and algebraic operation is exponential. So for instance, you take from the minus h1 and then you differentiate. You differentiate and you replace in the second line h2 theta 2 by y minus h1. And then at the end, after a series of manipulations, you eliminated the term EH2 theta 2. So that's what we do all the time. Okay. The nasty terms, which are exponentials or cosines of some unknown frequency and so on, by a differentiation and algebraic operations. And then at the end of the day, you get this nonlinear parameterization, capital Y equals some big vector. It's going to be a big vector, nonlinearly parameterized times a vector phi. Next slide, please. Next slide. I think you skipped slide 21. There's a slide 4.
So yes, slide 21.
21.
Is it? Yeah.
Okay, so we have more or less general results for two classes of systems. The one that is on top, which is motivated by mechanical systems. So second order differential equation with some exponential terms. And then we have another class, which is now an n-dimensional system, but where in the first case, you have the exponential entering into the state. And in the second case, you have the exponential entering into the output map. So in the measurement y. And then we have some more or less general results for generals f and g's. And at the end of the day, we recover this nonlinearly parameterization at the bottom of the slides. So you get some map W of some parameters eta and theta. Okay, next slide. Next slide, please. So let me just illustrate the first case with the recent work we do with Marcio de Queiroz from Louisiana State about the human shank dynamics. So this is the system. Next slide, please. So the system is a mechanical system that models the human shank. It's used for electric stimulation of human shank. And then you can, well, answering the question to this person, the exponential enters here in the model of the potential energy. So it turns out that if you want to model the human shank dynamics, the potential energy, which is this function u of q, has an exponential, and that's an exponential term that appears there. And exponentials appear also in Arrhenius laws, in chemical processes, appear in many, many instances of physical processes. So then you end with a dynamic system, which is j q double dot plus, and you see the exponential, where you have a term which is unknown, the parameter k2. Next slide, please. So then you need to know some prior knowledge and some technical conditions, and let me skip the details. So doing the operations that I described before, this differentiation, algebraic manipulation, you get a non-linearly parameterized equation, which is the one given here, y qualified transpose some matrix. Notice that you mix all the parameters. So in this map W, you get products of theta 2, theta 3, theta 2, theta 5, and so on. But then you use this scheme with DREM, and you can estimate only the first 4 equations, because you get, remember, you get scalar equations. So you can forget about these nonlinear terms if you use this DREM-based scheme. Okay? Yeah, of course you can use exponentials, but then you end up like the neural network people. They use exponentials and there's nothing you can prove. So the main result is that, well, at the end of the day, you use this nonlinear parameterization, you apply this least squares plus DREM estimator, and you get exponential convergence of your adaptive controller. And we compare this with the controller that was proposed before by Marcio de Queiroz, and the performance which was far better, because you get the linear error equation. Okay, next slide, please. So now, this is just a speculation. We're actually now trying to work with these people from differential algebra. And this is an example that I took up from from this book down here, where they do differential algebra and symmetry reduction operations. So they have this so-called Grossner basis operations. So these are algebraic and differential operations which go beyond just differentiation and algebraic manipulation. And you can, for instance, transform this system using these tricks, and you go to Maple, and it's a very complicated operations with differential algebra, and you can transform the system you have on top, where you see you have it's a linear parameterization, but the measure of state is x1, and then you have some nonlinear parameters in x2. And you can write it after some manipulations with these differential algebra tools in the form which is below, where you get everything in terms of measurable quantities. So the y, so you can use filtering, and then you can estimate. So we're currently working with people from INRIA in Lille to try to use these tools to go beyond our rudimentary tricks of just differentiation and swapping lemma and so on. Next slide, please. So let me talk about, I think I'm running out of time. How much time do I have now? Dean?
So, yes, so we have 20 minutes.
So let me skip this part. I would prefer to talk about the open problems, and this is just, let me just describe it very briefly. The idea is to propose new ways to parameterize systems which are different from the classical parameterization of parameterizing the vector field F, the matrix G, and then using properties of the system. In this particular work, what we exploit is dissipativity. So if the system is dissipative, then you can get parameterizations which are much simpler than just saying, I am going to reparameterize F, G, H, and J. What you reparameterize are the energy functions and the storage functions. And it turns out that you get much simpler parameterizations. This is reported in this journal. So let me skip all that, please. Go to slide, this slide, 32.
Yeah.
So this is a speculative series of slides that I want to share with you my thoughts. And I recommend this very nice paper by Anu Manaswamy and Sasha Plakov, which provides very, very deep historical perspective of adaptive control. I put it there because they add the word learning, but I see very little about learning in there. It's basically classical adaptive control. So let me go to the next slide. So let me first review some classical problems that I attention, which will probably go back to them and try to understand them. In direct adaptive control, there is very little new beyond the classical model reference paradigm for linear time invariance. For instance, nobody knows how to do adaptive PID, or beyond nonlinear and nonlinear parameterized systems, beyond the triangular structure. So we know this is a triangular structure. You have this very nice, powerful tool of backstepping, but this is not a physical parameterization. So there are no physical systems which satisfy these conditions. So I think this is an open problem. Do direct adaptive control, directly estimate the parameters of the controller and not go through the indirect route, which is what most of the people are doing. Another problem which I believe is open is time-varying parameters. There are some continuity results for a slowly time-varying case for many, many years. There's a result by Cui on slight variation of least squares for slow time-varying parameters. This is a student of Anaswamy, but it needs persistence of excitation and proves only ultimate boundedness. But still, this is an interesting step in the right direction. Then Alessandro and his student Chen, they have an alternative approach, which is trying to combine adaptive and robust designs. So you do adaptive to enter a certain ball of confidence, and inside this ball of confidence, you switch to robust designs. That's also an interesting route. And ourselves with Professor Pirkin from ITMO and Professor Isidori, we did some work on adaptive internal models. So that's also a possibility. If the time-varying parameter satisfies some internal model, then we can do much more than just arbitrary time variations. Now, for switching systems, there's a series of recent results. And it's interesting that these switching systems are actually a more general paradigm than what people are calling event triggered or linear parameter varying. These are just, as I should say, some fads and trying to cook up some new words so that people. The interesting thing is switching systems. And there's a formal solution without appealing to linear matrix inequality. So what people do is translate this problem into the feasibility of an LMI and claim that that is solved. That is not solving the problem. That's just translating the problem from one problem to another problem. So that's not very satisfactory from the scientific point of view. Next slide. So other approaches, well, if you assume that the systems live in compact sets and you can add projections and the nonlinearity satisfies some Lipschitz properties, that's what most of the people do, then you can simply inject high gain and dominate the nonlinearities. And these are complex, computational demanding methodologies, and they are not really adaptive, they're dominating nonlinearities. Then there is this fad of data processing-based approaches, neural nets, learning. In my opinion, there are no solid theoretical proofs, and I'm going to quote a couple of references. In the 1996 paper, I wrote the sentence which is below, talking about this explosion of neurofuzzy systems. And my contention, and I think it is still true, is that these works have not contributed at all to our understanding of adaptive systems. So they use classical tools, they use, whenever they do analysis, they do it with linearizations, with Taylor series expansions and things like that. Next slide, please. So let me just add 3 quotes that from recent literature. One is a paper from 2022, where they use neural network approximations to model the static map of a continuous stirred-tank reactor. And they claim at the end of the paper, they have to use 1,000 time steps for training. If you talk with chemical engineers, I talk with the needle Shan and so on, well, this is of course nonsense. You cannot submit the technical a reactor to 1,000 time steps. So this simply doesn't work. And then there's another paper on neural network solutions of PDEs, with at the end of the paper says, well, we can only approximate results and we cannot rigorously guarantee nothing. So this is the standing classical results that you read in these papers. Next slide. So let me quote one of the deepest thinkers of our community, Pramod Kargonecker, who in this recent 23 control systems journal, when he was talking about machine learning, I think this is a very precise statement. The machine learning techniques do not come with a deep understanding of how and why they work, as well as they appear to and when they might fail. So it's basically just proof by simulation or trust me, it's going to work and so on and so forth. Okay, next slide. I know that these are very hard statements, but it's a personal opinion, of course. Now, there's another trend in the community, people trying to revive old schemes like the famous Morse high order tuner. by several authors. Sasha-Bratkow's speed gradient algorithm has been taken again by Slotin et al. And adaptive dynamic programming. That might be interesting. So these old schemes, they were abandoned 10, 15, 20 years ago. And now people are picking up again and trying to combine this with new developments from optimization theory, which is quite interesting. Now, assessing the performance improvement of algorithms is also something that's been done by Jean-Jacques Slotin and Boffy, where they use this, well, this is a very trendy topic, the Bregman divergence, the Nesterov-Polyak accelerated gradient. Let me tell you a personal experience. I coincided with both of them, with Nesterov and Polyak in Moscow 4 or 5 years ago. And I asked them what did they think about their accelerated gradient schemes used for control. And I remember Boris simply laughed and said, "Good luck, Romeo. This is a very different problem from just standard optimization where you want to search the minimum of function, which is dependent of time. In our case, it is dependent of time. So it's not going to be easy, but I think it's still worth pursuing it. So there's this diverse, how shall I call it, discussion between model-free and model-based adaptation. Well, you have seen the previous comments. Another very interesting approach, I think, is this database identification. That's a completely different school of thought. It's not model-based, it's data-based. Not model-free, but data-based. And that's based on a series of results by Jan Willems, as usual, and deep thinkers like that. And the work of the Persis, for instance, is a good example of what can be done. And I think that's very interesting. So my conclusion of all of this is there a use of these techniques beyond pattern recognition? And I don't think so. I don't see it, at least now. Okay, next slide. So just to wrap up, I would like to end with a pessimistic note. And this answer to the question, is there a hope for a general nonlinear control theory? And the bad news comes from Lev Nikolaevich Tolstoy, who said, all happy families, and I use all linear systems are alike, every unhappy family, every nonlinear system is unhappy, nonlinear in its own way. So I really don't think there's a hope for a general nonlinear, not just adaptive, but general nonlinear control theory. So we can do a lot of things with the triangular systems, we can do a lot of things with forwarding systems, but the general theory, I don't think is possible. And we shouldn't aim at that. Thank you very much, guys.
Thank you very much, Romeo. Despite the technical problem, we had a wonderful seminar. And now question time. Anyone have questions? Please, you can directly unmute yourself and ask. Romeo, would you like me to stop sharing, or would you like to keep it?
Yes.
Okay.
Yeah, no, remove the slides, yeah.
Okay, I've stopped sharing.
Let me put my camera.
Romeo, some questions is on chat.
Yes.
On chat, you have a question. Please explain where exponential terms appear in practice.
I'm sorry, I cannot get my camera on. Yeah, so what do I need to do?
Okay, so we can read out the question for you.
Thank you.
So the expanding window which you introduced may not be robust in fast transient just because of the absence of forgetting. Is it possible to introduce forgetting in expanding window?
I think the question is related with something that Anu and Aswami and I have discussed a lot, is all these results, they lack a fundamental property, which is uniformity. So uniformity is a very important property. So all of them, they have a stability, global exponential stability sometimes, but not uniformly, because they depend on initial conditions. So that is true. That is a weak point of these results, that we don't have uniformity. I don't know if that's the answer to your question, but that is still an open question. And it is true that it's fragile in that sense, the lack of uniformity.
Thank you very much.
next question. Well, I think Alexander's question has been answered. Any questions, please, you can either type in or directly unmute yourself.
So is there another question or?
We're waiting for someone to either type in or unmute and ask. I actually quite like the approach you talk about when you're modeling the human shank system. So I actually have a very quick question, Romeo. Is this well, you talk about exponential and cosine sine. So can this method be applied to other types of functions, or what are the other type of functions you think this might work as well?
Well, these are the two functions which, in my opinion, are the ones that appear most often in applications. So as I said, you have Arrhenius laws, you have a lack of knowledge of frequencies is very, very common, but other kinds of, you mean non-separable parameterizations, well, you can think of arbitrary signs and so on, but we're motivated by physical applications, and we have been looking at physical examples where you get this kind of nonlinearities. And what we have encountered is precisely this exponential. So this exponential appears, for instance, in windmills. If you look at the windmill power coefficient, there's an exponential. If you look at the photovoltaic cells, you have an exponential also in the model. So this appears in many practical applications. But applying it to other nonlinearities, I don't know. The trick that we're using is really very elementary. It's just removing this nasty term, removing it by differentiation, algebraic operations. But I think, I really am very confident that with differential algebraic tools, we can do much better. We can do much better than that. So transform these equations into forms which are more suitable for our analysis, and doing this with Grossner basis operations, things like that. So we are now learning about this. It's not an easy task. It's a very impenetrable material for us, but we are working on this with Shirovira from Lille and the Nice team. So we're trying to do that.
Oh, thank you. Thank you. Are there any other questions? Okay, so I can't see any questions in the window unless there are any further questions. We'll wait for. Okay, so if there are no further questions, well, let's thank Professor Romeo Ortega. That's very interesting talk. Thank you so much. Zobe has a technical problem, but still, that's a very, very interesting talk.
I am really sorry. I should apologize. I am too old to learn new technologies. I'm sorry. But thanks for your patience.
Thank you very much, Romeo. And hope to see, well, by the way, later this, once this recording will be made available later on. Well, thank you so much, everyone. Hopefully to see you again next time in the next seminar series. Thank you all. Thank you.
Thank you. Thank you. Bye-bye.
Thank you.
Thank you, Romeo.
Thank you, guys. Bye-bye.